In this video, we're going to characterize R dotted with V cross B. Now, it is not at all obvious why we want to do that, okay? It just seems kind of arbitrary. But we're actually near the end, and I can give you a little bit of strategy for what we're doing. It doesn't explain why we're looking at this particular dot product, but it does explain why we're looking at a dot product. A dot product is a number, whereas a cross product is a vector. So when I take a dot product, I get rid of all the vectors. Now, because I'm working with functions of time here, what I'm going to get is, instead of necessarily getting just a constant number, I'm going to get a function of time, okay? But that's okay. I'm getting a scalar valued function. And I'm hoping that that scalar valued function is going to be defined in terms of r's and thetas. So what I'm going to do is I'm going to solve for this two different ways. I'm going to get two ways of describing it, set them equal to each other. I'm going to hope that what I get has just r's and thetas and constants in it, and then I'm going to try to solve for r in terms of theta. And if we are successful in that, what we will have is a description of the path our planet is taking in polar coordinates. All right, so the first method, I'm going to say that r dotted with v cross b is the same as r cross v dotted with b. Okay. Now, it may not be obvious why that's true. We didn't spend a lot of time looking at scalar triple products and how we could rearrange various things. So let me explain why this is the case. This is a scalar triple product. And remember, I could think of the scalar triple product as just being the determinant of the matrix that I would get that would have R, V, and B as its rows in that order. The vector I'm dotting, then the two vectors that I'm crossing in the order in which they appear. Now over here, cross product isn't commutative, but dot product is. So this is the same as B dotted with R cross V. And so that would be the determinant of the matrix that has B, and then R, and then V. So each expression is the determinant of a matrix that has R, V, and B as its rows. Okay. Now, there's a fact from linear algebra that some of you may be familiar with and some of you may not be. If you're not familiar with it, that's okay. That's why I'm explaining it. Okay. What it says is, if you have two square matrices that have the same rows, but in a potentially different order, their determinants are either going to be the same or the opposite. And it depends on how you would get from this matrix to this matrix. Basically, every time I interchange two rows, I multiply the determinant by a -1. So let's say I started with this, and I wanted to get to this. So I want B in the top. So I would switch B and R. So that's one row interchange. That changes the sign of the determinant. That puts B up here, but then I still have V here and R here. To get to this order, I now need to switch those two. Now that's a second row interchange, so that's two negative signs that I've introduced, and they cancel each other out. Okay. So, these are in fact the same, but R crossed with V is just B. Remember, we had determined at the very beginning of this very long problem that R crossed with V was constant. That was how we determined that our curve was going to be in some plane. So I'm going to get B dotted with B, and that's just the magnitude of B squared. Now, we had a couple different characterizations of B, but one characterization of B was that it was R0, V0 copies of K. And from there, we could see that the magnitude of B was just R0, V0. Okay. R0 and V0, this is a distance and this is a speed, so they're both positive numbers. Technically, I suppose I could say it's the absolute value, but these guys are both bigger than zero, so I'm just going to get R0, V0. Okay. So the magnitude of B squared is just R0 squared, V0 squared. So that's my first characterization of this scalar triple product. Now we're going to do it using a second method. And here we're going to take advantage of the work that we did in the last video, where we came up with this wonky characterization of V crossed with B. Now, because of the size of my whiteboard, I erased everything before I started this new video. So I'm about to write down the result that we got at the end of the last video. And if you're like, where did that come from? It came from the last video. Okay. So this is R dotted with. What we had gotten as our characterization for V cross B was GMU plus R naught V naught squared minus GM copies of I. Okay, so dot product distributes over this vector addition. So I'm going to have R dotted with GMU plus R dotted with R naught V naught squared minus GM copies of I. All right. For this first term, I'm going to remember that R I can write as R times U. R without the bar is the magnitude of R. That's the distance of our planet from the origin. And U is the unit vector that points in the right direction. So I'm dotting that with GMU. This R, this G, and this M, those are scalars. So I can pull those out in front. And then we're just multiplying that by U dotted with U. But a unit vector dotted with itself is just 1, because it's the magnitude of that unit vector, which is 1, squared. So this is just R times G times M. Now here, I'm going to again use the fact that I can just take that scalar and bump it to the front. And I'm going to use the fact that I can rewrite R as R times U. So I can say my second term is R naught V naught squared minus GM times RU dotted with I. Now off to the side here, I'm going to work out the U dotted with I. I can actually keep that R outside as well. I can take U dotted with I and then multiply it by R after I do the dot product. Okay, so if I look at U dotted with I, just as some side work here. Remember U was cosine of theta I plus sine of theta j, and we're dotting that with I. So the dot product distributes. That's going to be cosine of theta times I dotted with I plus sine of theta times j dotted with I. But I dotted with I, again, I'm dotting a unit vector with itself. That's just 1, so that's going to give me cosine of theta. J dotted with I is 0 because they're orthogonal. So U dotted with I is cosine of theta. So this second term becomes R naught V naught squared minus GM times R times cosine of theta. Excellent. So that's our second characterization of this lovely scalar triple product, R dotted with V cross B. So if I set them equal to each other, R naught squared V naught squared was what I got the first time. RGM plus R naught V naught squared minus GM times R cosine theta is what I got the second time I calculated it. Now I don't really care anymore that it's equal to that scalar triple product. I just care that these two things are equal. And notice, everything in this equation is either a constant, or it's R, or it's theta, where R and theta are my polar coordinates. And R appears once in both terms on the right and doesn't appear at all on the left, so I can factor it out. So R naught squared V naught squared is equal to R times GM plus R naught V naught squared minus GM times cosine of theta. Now if I want to solve for R, I'll divide by this. Now, in general, we don't like to divide by variables because what if we're dividing by 0? Well, here, this isn't going to be constantly 0 because cosine of theta is a function of time. If there are values of theta, that make this thing equal to 0, those values of theta won't be in our domain. And that could be the case, because if we are talking about something, kind of knowing that we're going to be getting a conic section, if I'm getting something where I've got the sun here at the origin, and I'm getting just a parabola or just a portion of a hyperbola, there are plenty of values of theta that won't show up in the domain for that. If we're actually talking about a planet, so that we're getting an ellipse, well, then there aren't going to be any restrictions on thetas. And that's just going to vary based on these initial conditions, but those initial conditions are precisely what's going to determine whether we have something that does get trapped in the sun's gravitational field or not. Okay. So, we will have R is equal to R naught squared V naught squared over GM plus R naught V naught squared minus GM copies of cosine of theta. Okay. Now, that does successfully solve for R as a function of theta. Everything else on the left is a constant. So that does give me a description in polar coordinates of the path that I take. What we want to show is that this is actually going to be a conic section, so that it's an ellipse or a parabola or a hyperbola, depending on what the initial conditions are. Okay. Well, in order for that to happen, I'm just going to remind you that we said for a conic section, we needed to get R was equal to E times D, where these were constants related to the conic section. And what's important is that they both have to be positive numbers. Okay. And E is the most significant one here for us. E is the eccentricity. The value of E, which must be positive, is going to determine whether we have an ellipse, a parabola, or a hyperbola. Okay. Over 1, and I said it could be plus or minus. In this case, we're going to be getting a plus E times cosine theta. If this plus were a minus, and if this cosine were a sine instead, that would also give me a conic section. But this is the version that we're actually running a good chance of actually getting. Okay. So, let's take a look. If I want this to match, I've got a number on top. I want to have 1 plus a multiple of theta. So I want that number to be 1. So I'm going to just do a little bit of algebra. I'm going to multiply this by 1 in the form of 1 over GM over 1 over GM. Okay. So we're going to have R is equal to R naught squared V naught squared over GM all over 1 plus. Now, this became a 1 because I divided by the GM. Now, I'm going to distribute the GM in the denominator here, so I'll have R naught V naught squared over GM minus 1 times cosine of theta. Now, the one thing that's left for us is I can figure out if this is going to work, my E, my eccentricity, is the number in front of the cosine of theta. That would be R naught V naught squared all over GM minus 1. Okay. And then the number that I have on top, that's supposed to be E times D. So that just means D would be R naught squared V naught squared over GM times E. That way, when I multiply it by E, I get this. Okay. Now, I can tell that this is positive, because that's a square, that's a square. The gravitational constant and the mass of the sun are both positive numbers. So, if E is constant, and this is if E is positive, and this is the product of E times D, then D is positive, so they're both positive. On the other hand, if E is negative, then D would be negative. They'd both be negative to give me this positive product. Okay. I need them both to be positive, or this doesn't represent a conic section. So I need to demonstrate that E is a positive number, that this is bigger than 1. Oh my goodness. That is what we will do in the next video. So we're almost there. We've got this formula that matches the formula for a conic section, except that we have to verify that these two constants, E and D, are actually positive constants so that we know that we get a conic section. That's our last step. That'll be our last video.